Let us now discuss some special rotor designs. Now the very first question is, why do we need a special rotor design? What is the purpose that it is serving? So if you see the torque speed characteristics, what we have discussed is going to look something like this, right? This is the synchronous speed. This is the torque axis, speed axis. Okay. So this is where we have the maximum torque. And what is the region at which we usually operate? In this region, the low slip region. Okay. But during the starting, the slip will be high. Here S is equal to 1. Here S is equal to 0. So under starting conditions, it will pass through this characteristic, and at the normal operating condition, this is the region at which it is operating. So this is the characteristic at one particular rotor resistance. Now if we increase the rotor resistance, then how will the characteristics shift? It will shift like this. The maximum torque value will remain same, but the position at which it will occur, that will change. Okay. So this is, let us say, R2 dash. R2 dash is greater than R2. Now what is the advantage of a high resistance circuit? When there is high rotor resistance, the starting torque will be high. So you can write, if rotor resistance is high, starting torque will be high. But what will happen? The region of operation is now along this region. So the slip will increase. That means at normal operation, the slip will be higher than it is when the resistance is lesser. So in this case, the slip is quite high under normal operating conditions. So when the slip is high, what will happen? The efficiency will be less. Why is that? The power that will be actually converted from mechanical to electrical to mechanical form, this is equal to 1 minus S times Pg. So smaller the slip, higher will be the energy that is converted. So we want our normal operating conditions to be at a low slip region. But if rotor resistance is high, then the slip will be high at normal operating condition, thus reducing the converted power. Okay. Therefore, efficiency will be reduced because of the high slip. Now, what if we reduce the resistance? If rotor resistance is small, then what will happen? We have to see this characteristic. Now, under normal operating conditions, it's fine only, but the starting torque, you will have lesser starting torque. Okay, starting torque will be less, but it gives good efficiency at normal operating conditions. So you can write, but efficiency is good at normal operating conditions since slip will be low. So this is how various values of rotor resistance will have an effect on the operating conditions. So how do we solve this problem in such a way that we get high starting torque also and we have good efficiency at normal operating conditions? That is where the special rotor designs come into picture. Okay. So we have two special designs here. One is the deep bar design and other is the double cage design. So we will see how each of them help in getting both the advantages. First we will start with the deep bar rotor design. So here how it is going to be, if this is the rotor, then usually let us say if the rotor bars are arranged like this. Okay. In deep bar rotor, what is going to happen? The conductor bars are going to extend deep inside the rotor. So what is the advantage of this? Say this is the stator and the rotor is here. The conductor bars are going to be placed here. Now what is going to happen? If you take the outer regions, so that means let us say this region of the conductor bar if you are taking. What is going to happen? The leakage inductance will be smaller as compared to a point that is deep inside the rotor. Why is that? Simply because this region is closer to the stator. What is meant by leakage inductance? It is a measure of leakage flux. So when this part is closer to the stator, more number of lines, flux lines will link with both the stator and the rotor. But here it is going to be having more amount of leakage flux. All of this leakage flux will be left out. But since this is closer, this will have lesser amount of leakage flux. Okay. So for this reason, the leakage inductance for regions closer to the rotor surface is lesser as compared to the regions deeper inside the rotor. Okay. So now what will happen? What is the effect of this on the torque? Under normal operating condition, what will happen? Under normal operation, slip will be small, right? And when the slip is small, the reactance will be negligible or much less compared to the resistance. Why is that? You have to remember the actual rotor circuit here, not the equivalent circuit. But if you remember, the rotor resistance is represented as R2, whereas the inductance is represented as S times X2, because X2 is equal to omega times L. Omega is the angular frequency, and we know that the rotor frequency is dependent on the slip, directly proportional to slip. So that is why we wrote as the Sx2. Okay, if you don't remember, just go back to the lecture and you can see this is the circuit that we got. Okay, so that means when slip is small, the reactance, this entire Sx2 will be smaller as compared to this rotor resistance. So what is the effect of this? If you take each of the conductor bars, you're going to have, this is the rotor slot, let us say, and this is the rotor surface. So all through this conductor bar, you're going to have a almost uniform resistance. That means the current flow will be easy. Okay, so basically it means that the resistance offered is less, meaning that low rotor resistance is observed under normal operating conditions when the slip is small. Now what will happen under starting conditions? Under starting conditions, what will happen to slip? Slip will be high. So now what you have, the conductor bar, if you take, if this is the towards the rotor surface and this is the deep end, and what will happen? The inductance that you will see here will be lesser as compared to the inductance that you're going to see here. And because the slip is high, here resistance will be negligible as compared to reactance. So the total impedance that you get, it will depend on the reactance. So since the reactance offered at this end is lesser than the reactance offered at this end, you can write down lesser reactance is offered at this end, and at this end higher reactance is offered. So that means what you have, the current will try to squeeze in through a narrower region. That means the effective cross section that is available for current flow is reducing. And this means that a lower rotor resistance is offered to the current that is flowing. Okay, so you can write current will try to squeeze into the lesser reactance region. Thus, the area of cross section through which current flows will be reduced. That is how the effective rotor resistance will be increased. So, if effective rotor resistance is being increased under starting condition only, under normal operation that is not the case. So, essentially what we are getting a higher resistance at starting and a lower resistance at normal operation. This is what we want. We want higher resistance at starting condition so that starting torque is more, and we want lower resistance at normal operating conditions so that the efficiency is more. So, you can write down here efficiency will be good, and here high starting torque is achieved. This is how you can get both of the benefits using the D-bar rotor design. Now, what about double cage? See, the theory is the same, only a slight difference in the way it is designed. So, if you take the rotor surface like this, you are going to have a small bar here, and then deeper inside you are going to have a larger bar. So, you are going to have small high resistance bars at the surface, the rotor surface. This is what we have. Okay, it is having a high resistance because its area of cross section is small, and you are going to have larger low resistance bars deeper in the rotor. Okay, so this is going to have a larger cross sectional area so that the effective resistance will be lesser. Now, every other explanation is same as the D-bar rotor. What is going to happen? Under normal operation, slip S is small, meaning that reactance is negligible compared to resistance. Therefore, current will flow uniformly in both bars. So, you are going to have lesser rotor resistance. This will give you good efficiency. Whereas under starting condition, slip is large. Here resistance becomes negligible compared to reactance. This implies that current will primarily flow only in conductors near the surface, and further these conductors are small, so still higher resistance is offered. Okay, so that means you are going to get higher rotor resistance, which will result in a higher starting torque. Okay.